Hello YouTube, this is the first in a series of videos in which we're going to discuss solving 3x3 or 3-variable 3-equation linear systems and kind of the basics of doing so. A little bit lengthier process than solving 2x2 systems, in which a lot of algebra students are used to, two equations and then the variables x and y. But a set of rules that we definitely want to follow and a set of characteristics that we're definitely looking for. So we're going to cover those in this video, starting with this. If you were learning to play a game such as, say, chess, you would want to first learn all the basic moves that you're allowed to make. And so we're going to start by taking a look at this. We're going to be doing what we refer to as Gaussian elimination. And, okay, this word Gaussian, okay, it comes from the name Gauss. Carl Gauss was kind of a big deal in mathematics. So we named it after him, but our three moves happen to be these. And the first move is this. We are allowed to interchange two rows. Now you're going to constantly hear me using the word row, but by row what I'm going to mean is this, an equation. Okay, so you're allowed to take, of your three equations, just swap two of them around. It's a totally fair move. The second thing we're allowed to do is scalar multiply a row. Now what I mean by scalar multiply a row is this. You're allowed to take an entire equation times, a constant. Alright, so like you could double all the coefficients and the constant in an equation and still end up with what we call a row equivalent system. And then the third move is this, and we're going to use this one constantly, but we say add a scalar multiple of one row to another row to replace the latter row. So basically we're saying we didn't do anything to the original row, but we're replacing the second row that we say, quote unquote, added that first row onto, or the scalar multiple of the first row onto. So you heard me use the words row equivalent system. We're going to take a look at this first situation here, but I say consider this first system right here, this variable 3-equation system. By the way, if you ever have as many equations as you do variables, you tend to be able to solve them, especially if they're linear. Say we want to find a solution to the system, that is a point, an ordered triple x, y, z, that when I plug it into any of these three constraints or equations, it makes them true. The fact of the matter is this. We say this system of equations right here is the same thing as this system down here, this equivalent system. So we say that this system here is row equivalent. And whenever we use the words row equivalent, what we mean is this. We've taken one system, done a series of our basic moves up here that we're going to call our elementary row operations. Okay, so these are referred to as elementary row operations, or EROs. Okay, elementary row operations. But if we commit a bunch of elementary row operations to a system, we get a new row equivalent system, which basically means that it's got the same exact solution as the original system. So why would I want to produce a new system? Well, let's take a look at the second system down here. You might have noticed that in the second equation it's missing the variable x, and in the third equation it's missing the variables x and y. And as a matter of fact, in the third equation we've already got our value for z. Z is equal to 2. So this stair-step pattern here, this stair-step pattern, you're going to notice two characteristics of it. First of all, it is stair-stepped, and the second characteristic is this. The leading coefficients of each row are 1. If it is in a stair-step pattern and the leading coefficients of each row are 1, we refer to this system as being in what we call row echelon form. Now, if you look up, the word echelon in the dictionary, you'll see it'll refer to, say, aviation sometimes, and it's kind of like how ducks fly in this pattern here, but this V pattern or something like that is kind of rows. It's tiered, T-I-E-R, tiered. Okay, this is what we're looking for, and the reason why is because if I had given this system to us, I said solve it. What we're going to do now is we could solve this over here, say, but we can back solve. And what we mean by back solve is this: since we already know z in the system, we could say, well, then for our ordered triple, we're already cool with this last part. The last part's going to be 2. So how could we find, say, y and x? Well, our method's going to be this. We're going to back solve by plugging this z into this second equation that only had two variables, y and z. So basically what we're looking at now is a situation in which we have y plus 3 times z is equal to 5, but now we're saying our z is 2. So we get y plus 6 is equal to 5, and therefore subtracting 6 from both sides, we have now y is -1. So now we have our y portion of this, and so now we're going to take these two values, our z, plug it back into our first equation, and take this y value. We're going to back solve by back substituting into a first equation, and we get this: x minus 2 times y plus 3 times z is equal to 9. And so for our y value we have -1. For our z value, of course, we had 2. And so now it produces this new equation, x plus 2 plus 6 is 9. So this is x plus 8 is 9. And the only number I can think of to add 8 to is, to get 9 is 1. So we say 1. So this produces one solution. So we're going to refer to this system as being a consistent system. This is very important we know the vocabulary. Consistent and independent. That is, in a further video we'll talk about what this really looks like in terms of graphical approach. But we say these are three planes that intersected at a single point, this single point here, but otherwise they're all independent of one another. They don't, overlap always. So let's take a look at a couple more of examples here. A 2x2 system, 2 equations, 2 variables, and then we'll solve a 3x3. Talking about how you want to show your work and whatnot, but using these equivalent row operations. Okay, so we're going to start with the system on the left here, and our job is to solve it using our elementary row operations, or EROs. But notice I said this: we want this two-tiered effect. Now we have two choices. We can eliminate our x's, or we can eliminate our y's. And a lot of people will be inclined to say eliminate y. I'm going to go for the x's here. But the important thing is this: I want to put it in that row echelon form where it's in that stair-step pattern where our first leading coefficient is 1 and our second leading coefficient is 1. We have something that looks like this. So the first thing I'm going to do is I'm going to use our first elementary row operation. It might seem silly, but I'm going to swap these two rows around. So I'm going to write x plus 2y equals 90 as our first equation, and we're going to write 2x plus y equals 90 as our second equation. Okay, again, I produced the new row equivalent system with the same solution as the original. All I did was switch these around so that I had a leading coefficient of 1. So now our next move is going to be this. I'd like to eliminate my x in the second equation, or eliminate everything that is underneath this positive 1 leading coefficient x. So to get rid of this 2 down here, I'm going to have to make my original -2. So you notice I put parentheses around this, and I say 2, and we're going to distribute this 2 here, negative. But really, I'm not going to write it like this. I just want you to see what it is that I'm going to do. I'm going to double the first equation, make everything negative, and I'm going to add that on to the second equation. But if you recall from our first page there, it said we're allowed to scalar multiply and then add it to another row to replace that other row. So we're replacing the second row here is really what we're doing. Okay. So that being said, what I'm going to do is this. I'm going to write -2 R1 plus R2 off to the side of row 2. This is me basically saying I'm going to double my first row, -2 really, times my first row, and add it to my second row, which produces this new row equivalent system that is this. Now, we negated doubled our first row and added it to the second. It doesn't replace my first equation. My first equation is still the same. My second equation now would be this. Consider if I took -2 times 1x and added it to 2x, that would be now 0x's. So that x underneath my original x here is now gone. If I took now this 2 times a -2, so 2y times -2 is -4y, and -4y added on to my 1y gives me -3y. And then if I took this times -2, this 90, this constant times -2, it would be -180, and -180 added on to my positive 90 in the second equation gives us -90. So now we have this thing that is in row echelon form, because our leading coefficients of each row are 1. Well, not yet. Actually, we need to now scalar multiply the second equation by -1/3. So we take -1/3 times row 2. Got ahead of myself there. So now we've got this new system, x plus 2y is 90. And the second equation would be just 1y is equal to -1/3 of 90, which is 30. Now we are in row echelon form, and it is also row equivalent because we used our basic moves there. It means it has the same solution as the original. Now that we have this, we can back solve our values in the last row up into each respective row above it. So we say y is 30, therefore our first equation would be x plus 2 times 30 is 90. And in other words, we say x plus 60 is 90, and this leads us to the fact that x is 30. So we have our solution to the system here. We say the point 30, 30, the ordered pair 30, 30, and it means this system is consistent as a solution, consistent system. And it's independent. So now using elementary row operations with a 3x3 system, it'll be a little bit lengthier process. I'm going to go kind of quick. You might pause the video at certain points, but let's take a look. Now, I don't need to rearrange anything here. The first thing I want to do is get a positive 1x in the first row, and we already have a positive 1x. Our job now is going to be to knock out the 2x and the 3x below it using elementary row operations, and so we're going to do two moves in one. That is this. We're going to say, well, 1x, what could I take at times to get it to cancel out with my positive 2x here? We're going to do this. We're going to take negative 2 times row 1, and we're going to add that on to row 2. We're also going to take negative 3 times row 1 and add that on to row 3. This is us showing our work here to produce some new row equivalent system. So let's start with the second row here. We'll do it in pieces, but we know this. That's definitely going to cancel out. You know, we'll rewrite our first equation here. We didn't do anything to it. It's still there. But the x in the second row is now gone. If we took the 1x in the first row times negative 2 and added it to 2x in the second row, it's now gone. Let's talk about our y. So if we took this y times negative 2, so it'd be negative 2y plus a negative y here. This would now be negative 3y. And we say, okay, so how about this? We got negative 2 times z is negative 2z. Negative 2z plus a positive z is negative z. And then negative 2 sixes is negative 12. Negative 12 plus a positive 3 is negative 9. Let's talk about our third row, where our 3x is now gone. We said negative 3 times the first row or equation, so negative 3 times y is negative 3y, plus a positive y is negative 2y. Let's change our color here, negative 2y. Negative 3 times z is negative 3z. Negative 3z plus another negative z is negative 4z. And then negative 3 times our 6 is negative 18, and negative 18 plus a positive 2 is negative 16. So here's our new row equivalent system. So now one might be necessarily inclined to make this into a 1. But here's the thing. If I took the second row times the reciprocal of its leading coefficient, so times negative a third, you're going to be dealing with some weird fraction here. So what I'm going to do is this. I'm going to take row 2, and interchange with row 3. And the reason why is because all the integers in the second or the third row there are even. And I'm allowed to switch rows around if I like. So we say negative 2y minus 4z equals negative 16, and negative 3y minus z is equal to negative 9. So now we're going to cause this to be a negative or a positive 1. So we're going to take it times its reciprocal. So we say negative a half times the new row 2 here. So if we do this, here's our new row equivalent system. X plus y plus z, first equation, is 6. We have our second equation, which is just y, plus 2z, which is negative a half of negative 4z, and is 8. And we say negative 3y minus z equals negative 9. So now we want to, since we have a 1 here and a 1 here, we're going to knock out everything below this y in the second row. So we need to knock out this negative 3y. So our ERO that we're going to do is this. We're going to triple our second row and add that to our third row. And we're going to write that system up here. But if we did this, triple the second row, add to the third row, we got x plus y plus z is now our new first equation. Not new, but we say y plus 2z in our second equation is 8. And then now our y in the third equation is now gone because we tripled our y in the second row and added it to the third row. So if we triple 2z here, 2z, triple it, 6z, 6z plus a negative z is 5z. We have 5z, and that's equal to triple our 8, okay, is 24, and 24 minus 9, that'd be 15. So now the last thing to do is to get a 1 here. So we'd say 1/5, or multiply by the reciprocal, 1/5 row 3. So now we have finally this x plus y plus z is 6, y plus 2z in the second row is 8, and now finally z equals 3, because 1/5 of 15 is 3 and 1/5 of 5z is z. What I want you to see is this. This video was about solving these things, and you're going to find a solution here. It's going to be consistent and independent, and I'll let you finish the rest of this equation. But the point is how to show your work and the vocabulary we use in order to get it into this new row equivalent system that we say is in row echelon form, in which our leading coefficients here are all 1, and we have this stair-step pattern. So cheers.